Okay, so as we finish up chapter one, I'm going to kind of condense all the last couple sections into one video here. So this might get a little bit longer than our normal one, but so it goes. Um, the last video, the kinetic and thermodynamic stability video, covered section 1.3. This video will cover sections 1.4, 1.5, and most of 1.6. There's a couple of things that are still there in the book. I encourage you again to go through chapter one. It's a nice review of the important concepts from Organic 1 and Organic 2. This will kind of get us started on a lot of that material. All right. So section 1.4 is getting started on drawing a mechanism. This is something that I think if you have taken a class from myself or Dr. Rubush in Organic 1 and Organic 2, you have seen plenty on how to draw a mechanism, right? Identifying bonds that are made and broken. This is something that you're familiar with. You can kind of see those kinds of things. One of the things that Grossman emphasizes a little bit is not being too distracted by things like bonds to hydrogen or pi bonds. Those aren't usually the most important bonds to identify when we're drawing a mechanism, just because um, pi bonds are usually either formed or broken as a result of other sigma bonds being formed or broken. And bonds to hydrogen tend to be very easy to kind of make and break. We can do acid-base reactions to make those happen. It's almost always easier to kind of catalog those hydrogens that have been added or subtracted from our molecule after we get kind of the heavier atom bonds that are made in there. And so just to kind of a re-emphasis, like look for the bonds between carbons and other atoms. Look for the bonds between heavy atoms that are made or broken. Those are going to be your signposts to kind of tell you where the reactions are occurring. Once we know where those reactions are occurring, we can break things down into what kind of transformation is happening. This we did in Organic 1. We talked about addition reactions, elimination reactions, substitution reactions. All of those definitions are essentially the same here as they were when we talked about it there, right? Addition reactions, you have two starting materials, for example, an alkene and HBr. They are combined into one final product. Elimination reactions go the other way. You have a compound that has a leaving group, you do an elimination, you generate the conjugate acid of that leaving group plus your alkene. So you take one starting material and divide it into two products. Substitution reactions, we're just swapping out one functional group for another. And then rearrangements are kind of a special case of where one starting material becomes one product, but we change the structure around a little bit. Rearrangements are definitely their own kind of chapter and type of reaction. We will talk about those a little bit more. Right, but rearrangements kind of avoid a lot of the nucleophile electrophile stuff that we've talked about, so they tend to be a little bit of a different beast, if you will. All right, my forward advancer is not working, so now we must advance. Okay, here we go. Classes of mechanisms. So we have the types of reactions that can happen, right? Addition reactions, elimination reactions, substitutions, etc. Each one of those can be through one of these types of reactions, right? We can do acid-base reactions or polar reactions. We can do radical reactions. Paracyclic reactions, again, are going to be these kind of cyclical movement of electrons. The Diels-Alder reaction or decarboxylation are two examples of paracyclic reactions that you have seen in Organic 2. And then we'll add on at the end of class this semester, we'll talk about metal-mediated or metal-catalyzed reactions. These use transition metals. We're going to get, these have a very different set of type of mechanistic steps. And so they're going to be kind of separated off from everything else that we talk about, right? Nothing really new here. You've seen radical reactions before, single electron reactions, chain reactions. We've seen all the acid-base polar mechanisms. That's 90% of what we talk about in Organic 1 and Organic 2. This is where we're talking about nucleophiles and electrophiles. This is where we're going to start. This is where we're going to spend most of our time in this course, right? About half the course is going to be polar reaction mechanisms. Okay? But recognizing which thing is true for our mechanism. Is our mechanism an elimination mechanism? Is our mechanism a radical process, right? Being able to recognize which reagents correspond to these kind of classes is going to be a big part of what we work on. All right, so let's talk about nucleophiles. My notes are on the wrong page, so you're going to hear some paper rustling as I fix that. All right, so nucleophiles. A nucleophile is something that has a high energy occupied molecular orbital, right? Highest occupied um, molecular orbital. If that's high energy, that's a good nucleophile, right? It's a high energy pair of electrons, right? The highest occupied molecular orbital, because it's occupied, that means that it is a pair of electrons that are available to make new bonds. Right? There are basically three types of nucleophiles that we're going to come across, right? Lone pair nucleophiles, pi bond nucleophiles, and sigma bond nucleophiles. The pair of electrons that we're identifying here, right? What is the highest occupied molecular orbital in a molecule? That highest occupied molecular orbital could be a non-bonding orbital, in which case it's a lone pair. It could be a pi bond bonding orbital, or it could be a sigma bond bonding orbital, right? So there are three types of orbitals that we could put it in. Could be a lone pair, could be a sigma bond, could be a pi bond. All of those are potentially nucleophilic orbitals if they are the highest energy occupied molecular orbital. All right, lone pair nucleophiles, these are the ones that you think of when you think of nucleophiles. These are things like, right, negative oxygens, neutral oxygens, negative nitrogens, oops, R2N, neutral nitrogens, right? R in these cases could be hydrogen, could be carbon, could be other things, right? We can also have more exotic things like phosphorus or sulfur, right? Neutral phosphorus, neutral sulfur, great nucleophiles. If you make those negative, even better nucleophiles, etc. Right? All of these things have lone pairs. Those lone pairs are the thing that's going to share with whatever the nucleophile is adding to, right? When we have heteroatoms, we tend to think of the lone pairs as the nucleophilic part of that heteroatom, right? So lone pair nucleophiles, usually heteroatoms, mostly these kinds of things. We can also have things like iodine is a great nucleophile, right? Iodine has plenty of lone pairs to share. Bromine is an okay nucleophile. It's a lot of lone pairs to draw, right? And etc. Chlorine, not that great, but okay. Fluorine is not a very good nucleophile because it doesn't share its electrons. Right? More on that in a moment, right? When these lone pair nucleophiles share their electrons with an electrophile, right, we end up with an increase in formal charge, right? So formal charge increases by +1 um, after adding to the electrophile, right? We convert the lone pair into a sigma bond that increases the formal charge of whatever atom is sharing that lone pair, right? If you take RO minus and you add it to a carbonyl, right, the oxygen of your nucleophile becomes neutral once you've done it. Right. So lone pair nucleophiles, I think, we understand lone pair nucleophiles pretty well. We've used those a lot in a lot of different contexts. Pi bond nucleophiles, these are also things that we've seen before. You can have alkenes, right? This is the very first pi bond nucleophile that we ever saw in organic 1. You take an alkene, you react it with an acid. That pi bond reacts with the H plus. That's the pi bond acting as a nucleophile. Alkenes react to form carbocations, right? We can have things like enolates. These are pi bond nucleophiles. Right? When we have a lone pair next to our enolate, right, these react to form, are next to our carbon-carbon double bond. These pi electrons can react with electrophiles that would create a carbocation at this carbon here, but because we have the oxygen next to it, right, that's going to form the more stable carbonyl resonance form. And so we make carbonyls, right? And this can be, we can have whatever else there, right? Doesn't have to be oxygen here. We can also have things like enamines, which we probably haven't talked about nearly as much as we should have, but you can have things like enamines where we have a nitrogen with a lone pair, right? This reacts the same way. The pi bond will go and react with whatever electrophile that's there. That creates a carbocation here that can be stabilized by um, the lone pair of the nitrogen. So imagine that we have um, an electrophile here. We can make this pi bond go get that electrophile, and we can get this, where we add the whatever the electrophile is to that alpha position and make the iminium ion as our resulting thing here. If one of these R groups is in a hydrogen, we can easily neutralize this, etc., etc. Okay, so we can use pi bonds as nucleophiles. We've seen this a bunch, alkenes and enolates being the main examples, although there will be others, right? Sigma bond nucleophiles, the only example we've probably really seen of these is organometallics, right? The classic is, of course, the Grignard reagent. If we have methyl Grignard, right, it's the sigma bond here that's going to share its electrons. We break this carbon metal bond. Um, I guess we've also seen things like sodium borohydride, right? This is another classic sigma bond. The sigma bond of this BH compound here, that becomes the nucleophile that reacts with the carbonyl, right? So these add to carbonyls, we make new sigma bonds, etc. And whatever the metal is, magnesium or boron, right? The magnesium becomes positively charged, the boron becomes neutral, etc. Right? So sigma bond nucleophiles, we haven't seen as many of these as we have pi bond nucleophiles or lone pairs, but they all kind of fit into one class, and that is the organometallic class. Okay, so the other thing that we want to talk about when we talk about nucleophiles is we want to talk about the difference between nucleophiles and bases. When we talk about the SN2 reaction versus the E2 reaction, this is always kind of a little bit of a sticky problem for Organic 1 students. Nucleophiles tend to have poor kinetic stability, right? So if you haven't watched the stability video yet, you should go watch that one, read section 1.3 so you know what we're talking about when we talk about kinetic stability. This just means they have a low energy of activation, right? Delta G double dagger, right? It's very easy to get nucleophiles to react with things, right? Bases, on the other hand, tend to have low, whoops, thermodynamic stability. Because when we talk about acid-base reactions, right, I'm talking about Bronsted bases here, just to be clear, right? Right. When we talk about Lewis-Bronsted acid-base reactions, we're always talking about, is the conjugate base more stable than the starting base? Is the conjugate acid more stable? Those kinds of questions and things. And that stability we're talking about there is thermodynamic stability, right? And so that means that nucleophiles have poor kinetic stability. That means that they have low activation energy. Bronsted bases have poor thermodynamic stability. That means that they have a low overall free energy, right? A low delta G naught. Or sorry, not low, high. Low delta G naught would be stable. Good bases are not stable, right? Okay, so it's very possible for things to do both of these things, right? We can have things that both have low kinetic stability and low thermodynamic stability. Those types of things are good nucleophiles and good bases. What's more interesting is when these two ideas diverge, right? What types of things are good nucleophiles but poor bases? What types of things are good bases but poor nucleophiles? So let's make a list. Larger atoms tend to be more nucleophilic, right? And tend to be less basic at the same time, right? So as the atoms get larger, as the elements get heavier, right, we are also getting to low electronegativity. Right? The lower we get in the periodic table, the lower the electronegativity is. What low electronegativity means is it's easier to share that pair of electrons. We've kind of started to talk about this in the sense of what that means is that our highest occupied molecular orbital is a higher energy orbital, right? So when we say low electronegativity, what we really mean is more nucleophilic, the higher energy occupied molecular orbital, right? These are all things we have identified as identifying nucleophiles, and that's still true here, right? The larger the atom is, the less steric repulsion it has with the groups around it, right? So we've got electronegativity, we've got steric repulsion, right? There's low electronegativity, there's less steric repulsion. Part of this is the bonds get longer, right? The bigger the atom is, the farther apart everything ends up being. And so other bonds are longer, other groups are farther away. Groups are farther away, right? And that reduces steric repulsion, right? The more steric repulsion we have around a base, the harder it is for that, the more kinetically stable it's going to be, the slower it's going to be to react, right? The more steric repulsion we add around our nucleophilic position, that means the harder it is for that nucleophilic position to get started in the reaction because it has to overcome that steric repulsion. So less steric repulsion means more nucleophilicity, right? And the opposite is also true, right? So when we get to basicity, make good bases, a way to make a good base for nucleophiles, right? First, we want smaller atoms, small electronegative atoms, and we want increased steric repulsion, right? So the opposite of what we're writing up here, right? If we have high electronegativity and high steric repulsion, then we're going to create good bases that are poor nucleophiles. The last thing that we'll talk about is resonance, right? So when we're talking about stabilizing things, we've got kind of the big three here: electronegativity, steric repulsion, and resonance, right? The more resonance is kind of a thermodynamic stability argument, right? So the more resonance we have, the greater the thermodynamic stability is going to be. The greater the thermodynamic stability is, the poorer the base is. But resonance doesn't really affect kinetic stability. And so resonance stabilization has very little effect on nucleophilicity. Nucleophilicity, right? But does make poorer bases. So it has little effect on nucleophilicity, but makes poorer bases, right? So having something that has resonance stabilization will tend to favor that thing being more nucleophilic as opposed to basic. Okay? So this difference between kinetic stability and thermodynamic stability, we can see examples of that. These are the same rationales and reasons that we've talked about in our previous organic courses. Electronegativity, steric repulsion, and resonance are the big three, or why are things more stable one way or the other, right? We're just kind of applying that now in the same way that we did. All right, so now that gets us to our last topic. We're moving further into section 1.6. These are electrophiles. So just like with nucleophiles, we can break up electrophiles into three groups: the Lewis acid electrophiles, and then once again pi bond electrophiles and sigma bond electrophiles. Lewis acid electrophiles, we've already kind of defined this. We defined this on the first day. Lewis acid electrophiles are those electron deficient atoms, right? Carbocations being the biggest one. Carbocations, um, we have neutral boron or aluminum, and then we have things like carbenes and nitrines, which are new. We haven't really even got to them yet. But of course, all of these have an empty orbital that can accept electrons. Whoops, pretend you didn't see that. Can accept electrons, right? So electron deficient atoms, carbocations, neutral boron, neutral aluminum, carbenes, nitrines, all of these have an empty orbital that can accept electrons. These are Lewis acid electrophiles, right? We make new bonds to these atoms without having to worry about it. Pi bonds and sigma bond electrophiles, again, what this means is we are reacting with the anti-bonding orbital, pi star, or the sigma star, the anti-bonding orbital of our sigma bond electrophiles. All of these are right. So we're breaking a bond as we add our nucleophile to the electrophiles, right? So in this case, with pi bond electrophiles, when the nucleophile adds and breaks a pi bond, carbonyls are the big example of this, right? Every time we add something to a carbonyl, right, our nucleophile comes in, we break that CO pi bond, make the lone pair on the oxygen. That is a classic. This carbonyl, this ketone here is a classic pi bond electrophile, right? This is how pi bond electrophiles work. You add a nucleophile in, the pi bond breaks and forms a lone pair on one of the neighboring atoms, right? Sigma bond electrophiles are leaving groups. So just like with the pi bond electrophiles, sigma bonds are going to, or sigma bond electrophiles are going to be things like this leaving group, where whatever our nucleophile is comes in here, we break that sigma bond and make a lone pair on the neighboring atom, right? Contrast that to the Lewis acid electrophiles. If we've got a carbocation here and our nucleophile comes in, there's no bond broken. All we end up doing is just connecting our nucleophile to, in this case, the carbocation that was there, right? So, oops, got to draw my results here. Nucleophile there, and then we get right, and we get that. So in the case of electrophiles, we can break bonds, we can break pi bonds or sigma bonds, and when we break those bonds, we're creating new lone pairs on the neighboring atoms, right? So as we go through these polar mechanisms, when we talk about nucleophiles and electrophiles, we will consistently see, right, it's going to be one of these three types of nucleophiles. Where are my nucleophiles, right? A lone pair, pi bond nucleophile, sigma bond nucleophile, reacting with one of these types of electrophiles, right? Now, one of the things that we're going to look at is under acidic conditions and basic conditions, which types of things can exist, right? For electrophiles, the only real determining factor is that Lewis acid electrophiles can only exist in acidic conditions, right? In order to have these electron deficient atoms, we can't have any bases around. And that kind of makes sense, right? Bases are going to have lots of electrons. They're going to share those electrons with any electron deficient atom that they see. And so any Lewis acid electrophile would immediately be reacted under any kind of basic condition. It would be very hard for this to form, right? Pi bond electrophiles and sigma bond electrophiles, you can think of lots of examples of pi bond electrophiles existing in basic conditions or acidic conditions, right? We've done carbonyl reactions under both basic and acidic conditions. We've done SN1 and SN2 reactions, sigma bond electrophiles, under both acidic and basic conditions. And so once again, you can do kind of the same thing there. So acidic and basic conditions don't really matter for pi bond electrophiles or sigma bond electrophiles, but for Lewis acid electrophiles, they do. And so this can, if we see that our reactions under basic conditions, we can cross out a category right off the bat. The other thing was we want to look at our nucleophiles and do more or less the same thing. And basically, nucleophiles don't react in general very well under acidic conditions. So acidic conditions tolerate weak nucleophiles, weak lone pair nucleophiles, and pi bond nucleophiles only. Right? You can't have organometallics under acidic conditions. Organometallics are too strongly basic. They will react with the acidic conditions, right? Instead of reacting with the thing we want them to react with. Pi bond nucleophiles, like alkenes, can react under acidic conditions. That's why alkenes create carbocations. Those carbocations are Lewis acid electrophiles, right? Enolates and enamines are a little bit more of an edge case. Usually those aren't going to exist under acidic conditions, although there are cases where that happens. And then the lone pair nucleophiles, if you have neutral compounds, those are usually okay under acidic conditions. Negatively charged compounds tend not to work there. So all of that is to say, oh, I pushed the wrong button. All right, sorry. All of that is to say, we've got electrophiles, nucleophiles, defined now. We've got categories for each one of them, and we're going to, as we do these reactions, we're going to identify which type of reaction we're looking at, what type of nucleophile we're looking at, what type of electrophile, and we're going to start to identify the patterns that come through there. This was a long lecture. I kind of condensed everything into one lecture or one lecture video to have that. Hopefully you made it through. That concludes what we're going to talk about from chapter 1. Now we're going to move on to chapter 2 and start looking at some specific polar reaction mechanisms.